Okay, so we're going to go ahead and take a look at how I can actually use this comparison theorem in an example, and also how I can maybe deal with this adjustment of what if this statement isn't true for all n. Okay, so let's take a look here at example number 1. Determine with justification whether this series converges or diverges. Okay, again, just for the sake of argument here, to help me kind of see what's going on, I'm going to write out a couple terms of this series. Sometimes you'll see in class that I do this, and other times I won't. But here, if I plug in the value of 1, you'll notice I get natural log of 1 over 1, which does simplify to be 0. The next thing up there would be natural log of 2 over 2, and then natural log of 3 over 3, and so on and so forth. So these are the numbers that I'm working with. I'm going to go ahead, though, and attempt to try to use a comparison theorem to help with this. And this can be a little bit tricky. So I'm going to start with the following. We note that the natural log of k over k. I'd like to try to simplify this in some way, because right now, this is maybe a series that's a little bit difficult to deal with. It doesn't seem to match any of the types of series that we've had before. And if you were to try to use any of the other tests that we've previously discussed, they either A, don't apply, or are very difficult to use. So I might try to think of a way that I might be able to make this series formula a bit easier to work with. Again, this is very similar to the comparison theorem that you worked with improper integrals. Here might be an idea. What if I just didn't have that natural log in the numerator? Then I would have had the harmonic series. Now, the tricky part here is I need to figure out what sort of inequality symbol, do I want to actually attempt to put in here? Right? Is it supposed to be greater than? Is it supposed to be less than? You know, like, how do I know which way to put this thing? I have no idea. But I can go ahead and try to think about, it seems like the denominators of these fractions are the same. The only difference is the numerator. So what I might want to know is the natural log of k bigger than the number 1? Okay, well, let's see. I know that natural log of 1 is 0. So definitely natural log of 1 is definitely smaller than 1. But what if I did something like natural log of 50, natural log of 500? If you were even to type some of those values into a calculator, you could quickly see that I get larger than 1. Over on the side here, I'm just going to sketch out a real quick picture of what the natural log function looks like. And remember, it crosses the x-axis at 1, and it hits the y value of 1 when it gets to the value e. Remember, natural log of e is 1. So you can see if I plug in anything smaller than e, I get something that's less than 1. But if I plug in anything bigger than e, I get something bigger than 1. So it seems like I could make the following argument. The natural log here is going to be bigger, but just not all the time, maybe most of the time. Maybe I could say for values of k that are ultimately, I guess, bigger than e. But of course, I don't want to state e because k is supposed to represent numbers in a spot in a list, and I don't have spot e. So if e is roughly 2.7-ish, then it seems like I would need to use values of k that are in spot 3 or larger. Okay, perfect. I have a comparison that's being made. So I note that the natural log fraction is greater than the harmonic fraction for k values that are bigger than or the same as 3. I'll also add on here that we know that the series of 1 over k diverges. Okay. The other thing I would need to double check is if I want to start to use this comparison theorem, I can go back and look at the conditions. I need to make sure that both the series now I'm about to work with have non-negative terms. So the first thing I check is 1 over k. Can that produce any negatives? No. Natural log, well, that's not going to produce any negatives unless I plug in something less than 1, and I'm not doing that. So I can see here that clearly natural log of k over k and 1 over k produce only non-negative terms. Okay, perfect. Now I can use the comparison test. So I can see that by the comparison test, the series natural log of k over k. Oh, I got to be a little bit careful here. I'm going to leave off where that value of k starts. I can see here that starting from the value of 3, I can make the claim that the series that uses this formula will be bigger than the harmonic. So I can claim that this is divergent. Notice again, the harmonic is divergent, and it's the smaller piece. And therefore, this thing up here is also going to be divergent. Now, I'll notice here that I haven't really answered the question, because the question wasn't, does the series that starts at 3 here converge or diverge? It was, does the series that starts at 1 converge or diverge? But of course, this is pretty easy to see how I can adjust for that. I can see that if I was to do 0 plus the natural log of 2 over 2 plus my series that starts at 3, notice again, I'm just taking those terms that I had up at the start, and I'm just kind of tacking them on. Here's thing 1, thing 2, thing 3. This is equal to my original series. And so I really have only deleted finitely many terms. And so convergence or divergence won't change. This is also divergent. Okay. This is sometimes a more confusing process when this value of k has to be changed. There's actually one spot in here where I just realized now I made a terrible typo and would need to be corrected. While it's completely accurate to say up here that the harmonic series diverges, we're not quite working with the harmonic series because we're working again by only considering what happens from 3 and up. But again, by the same line of argumentation, if the harmonic series diverges, then deleting the first 2 things off of it won't change divergence. Okay. All right. Let's go ahead and pause here and we'll take a look at example 2 in just a moment.